Bismillahirrahmanirrahim. Sallallahu alayhi wa alihi wasallam. Allahumma rabbi zidni ilma. Sallallahu alayhi wa alihi wasallam. Ameen. Alhamdulillahi rabbil alamin. Vectors. The topic of this lecture is equations of straight lines in vectors. For this lecture, I am using the work of one of my best students, Miss Sayyida Fiza Kaisar of class 2020, the Lyceum. An important advice for me and for everyone: speak well or don't speak. Vector equation of a straight line. This is the vector equation of a straight line. I discussed this equation after discussing this comparison and this example. Well, you all know this is the equation of a straight line in two dimensions in xy form. In this equation, x and y are the part of the equation, c is the y-intercept, and m means gradient, and this is the formula of gradient. You can either use this or this. Since this formula is in two dimensions, therefore we are unable to find the equation of a straight line in three dimensions in xy form. There is no formula of gradient. Therefore, we use vectors for the equation of a straight line in three dimensions, because the alternate of the gradient in vectors is the direction vector. This q means the direction vector of the line, and this is the alternate of the gradient. And we can find q in three dimensions we can find q either by using this vector AB or BA. If we have 2 points on the line, then we can find q either using this or this. If we use this, then the answer will be OB minus OA, and this will be OA minus OB, and both the vectors are multiple. So we can find the equation of a straight line in three dimensions only in vectors. And this is the equation of the straight line in vectors. In this equation, both r and t are the part of the equation, like y and x are the part of the equation in this equation. We only substitute the values of m and c in this equation to get the equation of the straight line in xy form. Whereas in this equation, we only substitute the values of a and q to get the equation of the straight line in three dimensions in vectors. I already have told you about this q. This q means the direction vector, and this is the formula of q. Either use this or this. This a means the position vector of the known point. If we have 2 points on the line, like a and b, then we can either use a here or b here. Like in this equation, we find the equation either by using this point or this point. This is the example of the vector equation in a straight line in three dimensions. Find the equation of a straight line that passes through the points A and B. See, these points are in three dimensions. To get the equation of a straight line, we need two things: the direction vector and one known point. Since we have two known points, so we can either use A or B. Number one, number one, we just state that this is the equation of the straight line. If you are using point B, then straight B here. If you are using point A, then straight A here. So there are two ways: either use B or A. I've done both the methods. So Q, I told you this is the formula of Q. Q is AB, vector AB. Or you can use Q as BA. They both mean the same thing because both the vectors are multiples. So if you are using AB, then it will be OB minus OA. And this is the value of Q. So this is the equation of this straight line. We just need to substitute Q and B. So this is B and this is Q. This is the equation in column vector form and column vector representation. And this is the equation in IJK form. This will become 4i, 5j, 7k. T is here, and this vector will become 3i, 3j, and 4k in ijk form. What if someone is using this formula for q, then he would get this vector. And if he is using the point A, then he needs to write the coordinates of A here in position vector form. So his equation would be like this. These two equations are same. Why? Because these 2 points are on the line and these two vectors are multiples. I discuss this thing after discussing this thing, vector equation of a straight line. So this is the vector equation of a straight line. We have done an example of this, and this is the rough sketch of this line. This A means the point A, the known point A on the line. In vector form, we write this as OA. This vector as OA. In small letters, we can write OA as this small a. So this A means position vector of the known point on the line. This is here. This R means any point on the line. That is why its coordinates are x, y, and z. And since this is the known point, so the coordinates are x1, y1, z1. And you can write this in vector form as OR. So OR means small r. You can say this. OR is small r. And this r is here. And this q means the direction vector of the line. This is the alternate of the gradient. And this t is the scalar multiple of q. We only substitute the values of a and q in this equation, and we leave r and t as it is because these two are the part of the equation. See, OA or small a means position vector of the known point, given point. T means the scalar multiple. Q means direction vector, which is the alternate of the gradient. Direction vector of the line. You can say this. It is the direction vector of the line. And the formula of Q is AB or BA. And this R means the position vector of the known point. Variable point. This means any point on the line. If C is unknown, if C is here, maybe here, and if it's unknown, then the coordinates of C will be x, y, and z. So if C is unknown and it lies on the line, then R will be replaced by OC. This is very important. If any point is unknown, then R will always be replaced by that point because the coordinates of R is xyz, and the coordinates of the unknown point will also be xyz. So we can write OR as OC. So this is very, very important. Make sure you always replace R by the unknown point whenever a point is on the line and is required. Unknown point. We already have discussed this comparison in 2 dimension and 3 dimension. We have discussed this example as well. I left this concept. Well, this means this is x, y, and z. This is basically z. So if C is unknown, although we have discussed this here, but I would like to discuss this here again. So since C is unknown, C lies on this line. Therefore, you need to replace R by C. This is R. It's here. So OC will be R. And if you add these two vectors, you'll get this thing. So this is the position vector of the unknown point on the line in terms of t. This is very important. If any point lies on the line and it's unknown, then always replace r by that point, and always add these two column vectors to get the position vector in terms of the scalar multiple t, for example, in this case. Well, vector equations of two lines. For direction vectors, these are the vector equations of two lines L and M. I discussed these two equations after the discussion of these things. Well, for direction vectors, we have two letters, P and Q. We can only use these two letters for the direction vectors. That is why we have P here and Q here. Direction vectors are always multiply with the scalar multiple. This T means scalar multiple, this S means scalar multiple. So this Q means direction vector of line L, and this P means the direction vector of line M. So for direction vectors, we have just two letters, P and Q. For scalar multiples, we have two letters, T and S, and two symbols, lambda and mu. Here we have T and S. We could have lambda here and mu here. So for scalar multiples, only four things are available, two letters and two symbols. And for position vectors of the given points, they can give you any point, A, B, C, D, E, F, whatever. In fact, N as well. So make sure you understand these four things carefully. This T means and this S means these scalar multiples, and this Q and P means the direction vectors of both the lines. I'm sorry. Well, when a point lies on a given straight line, unknown point, if B is unknown and lies on the line, then this vector, this is very important, this is the direction vector of the line, this is the known point of this line, and since maybe B is known or unknown, let's suppose B is known. If the point B, which is known, lies on the line L, then this vector AB should be multiple of the vector Q. This is the way to verify whether the point lies on the line or not. If this vector AB is multiple of the direction vector, then this means this point lies on the line. If AB is not multiple of this vector, that means this point does not lie on the line. This is the way to verify whether the point lies on the line or not. This is here. Find whether this point C lies on this line or not. Let's suppose this point is A. This is the direction vector. So first we need to find AC. If C lies on this line, then this vector AC must be multiple of Q. And how would we find AC? See, AC will be OC minus OA. So it is minus 311. If you see AC, if you compare this AC with the direction vector, with this vector, then you will see that these two vectors are not multiple. Since minus 311 is not multiple of this vector, that is AC is not multiple of Q. Therefore, C does not lie on the line. Therefore, this point C does not lie on the line. So there are two methods. This is the method 1 and this is the method 2. The student replace this C here, and this is AC in fact. This is C and this is A. So this will become vector AC. So you have two options, either find AC separately or substitute C here. This vector is AC and this is not multiple of this vector. Therefore, this point C does not lie on the line. Either use this or this, both the methods are fine. This is one of the most important concepts of vectors in lines. Point to line shortest distance. This is point to line. Shortest distance means the perpendicular distance. Now let's understand this concept through this example. To get the perpendicular distance or shortest distance from the given point B to the given line L, use this sketch. Make a rough sketch, this one. The two things will be given. The point will be given and the equation of the line will be given. And you need this distance. This is the point to line distance. And this is the requirement. The problem is this point F, which is the foot of perpendicular from B to this line L. Since this point is unknown, so first we will work for F. There are 3 or 4 steps. Number 1, work for F and then work for vector BF. When you will find BF, it will be in terms of T. Then you need to work for the scalar multiple T. And after getting the value of T, you will substitute T in the vector BF and then you will find BF. So there are three main steps or three more very important things. Number 1, work for F. The first step is find the vector OF. And how will you find vector OF? This is so simple. I already have told you all that this point is unknown. Since F is unknown, therefore R, this R will be replaced by OF. See, OF is in terms of T because R and F, they both have same coordinates. So OF is this. OF is R. Let me write the equation of the line because I am solving the example. So this equation will be given. In exam, they will give you two things, the point and the equation of the line. Let's suppose this is the equation of the line L. So when you will when you will simplify these two vectors, then you will find OF in terms of T. This is OF. So the first work is over, which is the vector OF. This is vector OF. Now the second work is find vector BF. BF is so simple, it's OF minus OB and it will be in terms of T. This is OF and this is B. They will give you vector B, they will give you point B. Let's suppose point B is 5, 7, 2. They will give you this point. So you can easily get BF in terms of T. Now the problem is BF is in terms of T. How will you find T? See, this vector BF is perpendicular with this vector Q. Therefore, the dot product of these two vectors BF and Q will be 0. We have discussed the dot product in the first lecture that if two vectors are perpendicular, then their dot product is always 0. So for T, this is the step number 3. You are working for T. So for T, take the dot product of these two vectors. Since these two vectors are perpendicular, therefore their dot product is 0. And with the help of this, you can get the value of T. Once you get the value of T, substitute T back into BF. Then you will get BF in the known form. Let's suppose 1, 2, 3. And after getting vector BF in this form, just find its magnitude. And this would be the answer. So let me give you a short review of this concept. Point to line shortest distance. Two things will be given. A point will be given and the equation of the line will be given. And this is the rough sketch, and this sketch will help you to understand this concept in detail. So first suppose this F, this is the foot of perpendicular from the given point B to the given line L. And there are three main steps. Number 1, work for OF. Since F is unknown, therefore it will be replaced, the R of the equation will be replaced by OF. It's here. And this is OF in terms of T. This is OB in vector form. This is now B, and you can convert this in the vector form as 5, 7, 2. So this is OB. So we have OF, we have OB, we can easily get BF. But since OF is in terms of T, therefore this BF will be in terms of T. Now the problem is T. How will you find T? Since BF is perpendicular to Q, this vector is perpendicular with vector direction vector Q. Q means the direction vector. This is the direction vector Q. So since these two vectors are perpendicular, therefore by taking the dot product of these two vectors, we can easily get T. Once you get T, substitute T back into BF and get the BF in known form like 1, 2, 3, for example. And then get its magnitude, 1 square, 2 square and 3 square. That will be the final answer. Now let's understand this concept through this example. Find the shortest distance from B, this point, to the line L, and the equation of line L is this. Now first make a rough sketch. B is here and this line is here. And this is Q, the direction vector of the line. It's here. And this is the foot of perpendicular, X, Y, Z, from B to this line L. Now number 1, first work for OF. This is the step 1. So OF will be this. OF is R. This is OF. Now work for vector BF. So it's simple. We have OF, we have OB, we can easily get BF. This is BF. Now the problem is BF is in terms of T. Since BF and this vector Q are perpendicular of each other, therefore their dot product must be 0. For T, this is step number 3. This is step number 2. And this is step number 3. Work for T. And T, you can find T by taking the dot product of these two vectors. So by taking the dot product of BF and Q, we have T. It's 1 upon 7. Now after getting T, substitute T back into BF. Put this into PF, vector BF. So this is vector BF. Now just find its magnitude. And this is the shortest distance of point B from line L, B to L. If you want to see the solution again, you can. Step 1, find OF. Step 2, find BF. Step 3, work for T. Get the value of T and then substitute T back into BF. This is BF. When you will put this T here, you'll get this BF. And this is the shortest distance, BF. I hope you have understood this concept very well. Now, the next thing, scalar product. We have done this scalar product formula in my first lecture, lecture 1A. But just for a review, see this example. If A is this and B is this and we need theta, first get A dot B. And you know how to get A dot B. Multiply 2 with 5, 1 with 1, 3 with -2. We multiply the corresponding components of both the vectors. X with X, Y with Y, Z with Z. And we always put positive sign. 2 5s are 10, then put plus sign. 1 1s are 1, then put plus sign. And 3 to the -6, it's here. Since dot product is positive, so the angle is acute between these two vectors. This is the formula of the dot product. Get the magnitude of A and then magnitude of B. Substitute this 5, this and this into this formula. And this is the angle between these two vectors AB. And it's acute. This is the next important topic of this lecture, of this chapter in fact. Consistent and skewed lines. Consistent means lines intersect and skewed means lines do not intersect. That's it. In 3 dimension, non-parallel lines may or may not intersect. If lines intersect, then they are said to be consistent. Otherwise skewed. So when lines intersect, they are consistent. When lines do not intersect, then they are skewed. And how will we prove this, whether the lines are consistent or skewed? See, this is very simple. Let's understand this concept through this example. Find whether the lines L and M intersect or not. And these are the equations of these two lines, L and M. You just need to suppose if lines L and M intersect, then they will intersect at the common point. What if lines intersect? Then they would intersect at a common point. So their R must be same. I mean, this R must be equal to this R. This is the common point. Now, by equating these two R's, we have these two equations. I mean, these two things. This is the R of the first equation and this is the R of the second equation in the simplified form. We added these two vectors. So now we have 3 equations, 1, 2, 3. We will solve any 2 equations for the values of S and T. And then after getting the values of S and T, we will substitute the values of the S and T into that equation which we did not consider while solving. If that equation would verify, that means lines are consistent, otherwise skewed. Okay, this is equation 1, this is equation 2 and this is equation 3. I'm solving 1 and 2. You can solve any two. 1 and 3, 2 and 3, 1 and 2. I'm solving 1 and 2. By solving 1 and 2, we have these values of S and T. Unfortunately, I'm getting same value. Normally, we get different values. Like S is 1, T is 3, let's suppose. So, this is the value of S and T. Well, since we use 1 and 2 for solving, therefore, I will substitute the values of S and T into equation number 3, which I did not consider for solving. So, by substituting the values of S and T into this third equation, we see that this equation is not verifying. Therefore, the lines do not intersect. Hence, lines are skewed. What if both the sides are same of this equation? That means the lines are consistent. This is the extra work. If lines are consistent, if both the sides were equal, Then for this point of intersection, we substitute either S here or T here. If this equation would verify, then we substitute either T here or S here to get this position vector of their point of intersection. If lines are consistent for position vector of their intersection, either substitute S or T into equation 1, this is equation 1, or equation A. You can say this is equation A. And this is the point of position vector of the point of intersection. And if they ask find the point of intersection, then give your answer in coordinates form. Now let's solve one question or discuss the solution of a question from the worksheet. This is a very good question. Question number 3. The lines L and M have vector equations. This is L and this is M. Show that L and M intersect. So when lines intersect, they will intersect at a common point. Therefore, their R must be equal. So by equating this equation with this equation, we have this equation. Now we just need to solve any two equations. We have three equations, 1, 2, 3. You can solve any two. I'm solving this and this. And I'm getting these values of T and S. Now we have to check whether the lines intersecting or not. In this case, we have to in fact prove that the lines intersect. So by substituting the values of S and T into this equation, we have this. This equation is verifying for these values of S and T. Since this third equation is verified, therefore we say lines do intersect. This means lines intersect, or you can say lines are consistent. Now for the position vector, if they ask find the position vector of their point of intersection, then this is the equation A. You need to substitute either S here or T here. So by substituting S minus 1 here, we have this position vector. This will become 0, this will become 2, and this will become minus 1. This is the position vector of their point of intersection. And this is the point of intersection. If the question is find the coordinates of the point of intersection, then give this answer. If they ask find the position vector of their point of intersection, then give this answer or this answer. So I'm just giving you a short recap. First, equate both the R's, get three equations, solve any two. I solved these first and two second. By solving these two equations, we have the values of S and T. By substituting the values of S and T into this equation, which I did not consider for solving, this equation is verifying. This means lines do intersect and lines are consistent. And if they ask find the position vector of their point of intersection, then you have option either substitute T here or S here. I substituted S here and I got this thing. If they ask find the point, there is a difference. Position vector and point. Position vector means give your answer in vector form, and point means give your answer in coordinates form. Just convert this in coordinates form. Well, let me discuss one question of shortest distance. I think it was question 1, I guess. No. Shortest distance question. Yeah, this is the shortest distance question. We have done this topic. Well, the question is the point P has coordinates, this is P, and the line L has equation. Find the shortest distance from P to L. Number one, make a rough sketch. This is P and this is the line L. And this line L has this equation, and this is the simplified form of R. Well, we need this distance, PF. This is the foot of perpendicular from P to line L. And the problem is F. F is unknown. I told you there are three main steps. Number one, work for OF. This is the step number one. First get OF. This is OF. Since F is unknown, so replace R by OF. So you can say this is OF. It's here. Number two, work for PF, vector PF. This is PF. OF minus OP. So this is vector PF in terms of T or lambda. This is the scalar multiple. We can have T here, lambda here, mu here, or anything else. Now the next thing is, since this PF is in terms of lambda, therefore we need the value of lambda. This is the step number 3. Take the dot product of these two vectors, PF and Q. Since these two vectors are perpendicular, therefore their dot product must be 0. This is Q. It's here. So by taking the dot product of these two vectors, we have this and we have the value of lambda. Now after getting the value of lambda, substitute lambda back into this equation, PF. This is PF. And this is the magnitude of the PF. So first work for OF, and OF is R, it's here. Then work for PF, it's here. And then see, PF is perpendicular with Q, so take the dot product of these two for the value of lambda. And then substitute lambda back into PF and get PF, and then get the magnitude of PF.